maybe give a little practice here in a short example. Let's say I give you this sequence. It might look familiar because we just saw it. Two things I want us to do. Part A, write an expression for a sub n and find its limit, and then determine the sum of the infinite series. So let's focus our attention on that. To write the expression for a sub n, we simply just look at our terms in our sequence, and we decide that we notice some things that are happening. We have a fraction for each term, and it seems pretty clear that the numerator is just 1 each time. But if we look in the denominator, 2, 4, 8, 16, upon careful inspection, we probably can come to the conclusion that that's just some exponent of base e, or base 2, base 2. So we have 2 to the first, 2 to the second, etc. So if we want to take this limit as n approaches infinity of 1 over 2 to the n, we're going to get 1 over a really big number, which we know to be 0. Now, if we move on to part B, a little bit more exciting question, determine the sum of this infinite series. Well, you might already know the answer because we looked at it geometrically. What we're going to do now is just build that sum just the same way that we did before. You saw these sums earlier with the geometric demonstration. But now I can use my 1 over 2 to the nth power as my a sub n. And what that will enable me to do is to find a formula where 2 to the n seems to be the denominator in each of those partial sums. And then for the numerator, 1, 3, 7, 15, you would just subtract. So there you have it. Now you could just split this thing apart very easily. Realize that the first term is 1, and when you subtract 1 over 2 to the n, and then think about throwing a limit in there as n gets really big, you're just going to get with that 1. So, a couple of key points to remember before we wrap up. A sequence is just an ordered listing of terms. A partial sum is a running total of the sum of the terms in a sequence. And then finally, if the sequence of terms that make up the partial sum has a finite limit, then we can say that the infinite series will converge to that limit. And this just lays the groundwork with awesome things that are about to come your way with the rest of the topics from Unit 10. We hope to see you there. Take care and keep studying. Welcome back, BC students. We're going to now take a look at the test. So, our key points to remember: when implementing the nth term test for divergence, you're always looking for the limit as n approaches infinity to be anything except 0. A limit result that's equal to 0 just simply means that the nth term test for divergence is inconclusive. So it just means that you're going to have to use another test. And I've been referring to this test as the nth term test for divergence for a reason, because it only reveals whether a series diverges. And it's something that's really important to learn. I certainly hope this helps. You're now 2 series tests in. We're going to have some fun talking about a few more series tests in the upcoming videos. And as always, we want you to stick around for those. But in the meantime, keep studying those series. We'll see you. Welcome back, APCAP PC students. Mr. Record here for video 1 from topic 10.4. As you can see, we're going to talk about the integral test for convergence. And our focus in this video more so is about the three conditions that must be met in order for this test to apply. If you're interested in seeing exactly what the integral test does and what it looks like, then you want to tune in to daily video number 2 over topic 10.4. Once again, my name is Tony Record, and it's a pleasure to be with you on this beautiful day talking about integral tests. So what are we going to learn here? Well, as I said before, this is something very new. It's something that falls on the heels of the improper integral, as you're going to see. And basically, in a nutshell, this is going to serve as our third convergence test that we've learned at this point. And what it does is it starts off with this condition. It says if we've got a function that's positive, continuous, and decreasing for some x greater than or equal to m, where n is a positive integer greater than or equal to 1, and we can let the nth term expression be equivalent to this continuous function f of x, then the following is true. The summation of that nth term expression, so in other words, our infinite series will sum and have the same behavior as our improper integral of f of x evaluated from 1 to infinity. So they have the same behavior. So basically, in a nutshell, it's saying whatever this improper integral does, this series is going to do the same thing. So as you can tell, you're going to have to know what is the behavior of this particular series, or this particular quantity, this improper integral first, which is going to take you way back and working a little bit with Unit 6 ideas at the end of that particular time. Now, as you can see, there's a lot of language going on in this problem. So note that there are three conditions that must be satisfied in order for the integral test to apply. And that is something that the College Board, the Advanced Placement Calculus exam, is going to be very, very interested in seeing if you know. So what are those things? Function has to be positive, our function has to be continuous, and our function has to be decreasing. And remember, once again, when I say our function, you can basically take whatever expression that you have here and just equate it to f of x. That way you're a little bit more used to using these calculus ideas with that f of x, and then you can apply those three ideas a little easier. Let's go ahead and practice a little bit and see if this makes sense. We're going to use the integral test, but again, our example 1 here is really just to confirm whether or not the integral test can be applied. So our first example is going to look at the summation as n goes from 1 to infinity of n over n squared plus 1. So you got to think, what are those criteria? Well, number 1, we're first of all going to equate our nth term expression, that's n over n squared plus 1, and let's just call it f of x. Let's make it easy. Let's call it x over x squared plus 1. Do you have to do that? No, you don't. If you just refer to it as n over n squared plus 1 and think of that as connecting the dots and being continuous, it will work. This might be a little bit easier because you're typically used to dealing with functions like f of x that are continuous. So, first, is f of x positive? Well, it certainly is, right? No matter what values you would plug in, starting at 1 up to infinity, this is always going to take on a positive answer. So you can just simply state that's true. And it's nice if you can state this condition because we'd like to know specifically when this is true. Is f of x continuous? Sometimes it's a little tougher to decide. Are we continuous or not? Well, if you look at the denominator and you don't run into any situations where the denominator would be 0, there's a very good chance that we're going to have that continuity, and that's going to be true for the entire life of this function for which it's defined to start, which is when n is 1, or in our case of our function x is 1. But now, test 3, that's the one that's a little trickier because you may not be able to readily tell if this particular series or this function is going to be decreasing. So one great way to do that is to rewrite it in a little bit more applicable form that we might be to dealing with functions like f of x that are continuous. So, first, is f of x positive? Well, it certainly is, right? No matter what values you would plug in, starting at 1 up to infinity, this is always going to take on a positive answer. So you can just simply state that's true. And it's nice if you can state this condition, because we'd like to know specifically when this is true. Is f of x continuous? Sometimes it's a little tougher to decide, are we continuous or not? Well, if you look at the denominator and you don't run into any situations where the denominator will be 0, there's a very good chance that we're going to have that continuity, and that's going to be true for the entire life of this function for which it's defined to start, which is when n is 1, or in our case, our function x is 1. But now, test 3, that's the one that's a little trickier, because you may not be able to readily tell if this particular series, or this function, is going to be decreasing. So one great way to do that is to rewrite it in a little bit more applicable form that we might be able to take a derivative. And now you're going to get a wonderful workout, because we're going to go back to a unit 5 idea that's going to talk about how do you tell if a function is going to decrease. And that is if the derivative is negative. So we take this derivative. Hopefully the product rule doesn't bother you too much, because that's what we're certainly going to use there. Also, keep in mind that this piece right here has a bit of a chain rule that had to be used. That's where this 2x came from. Now, you're also going to get a little bit of a workout here in being able to simplify some of these expressions. So notice the right side of this term, or this expression, I should say, needs a little bit of help. So I clean this up a bit by multiplying my 2x and my x. I can bring that negative out in front. And then I can make something very interesting in that you can factor x squared plus 1 to the negative 2. If I do that, then the x squared plus 1 that's left here is going to be raised to the first power. Because after all, negative 2 is negative 1. And I have minus 2x squared, that's only remaining second. Now we have it made. Now we can simplify the contents within the brackets. I can move down that term that has the negative exponent attached. And then it's probably pretty clear that if x is a value larger than 1, I have a negative value in my term. The denominator is always positive, but that numerator, you can see, is going to take on a negative value when x is bigger than 1. And as long as we are going to be increasing at some, or decreasing at some point for a value of x, and remain decreasing, that we have met criteria number 3. So our integral test could be applied. We'll apply the integral test. Let's take a look at another real quick example of how we can use the integral test to determine if it applies. So let's confirm whether or not the test applies to this guy. The summation as n goes from 3 to infinity of n over the square root of 2n minus 5. Well, once again, we define our f of x. We very clearly can see that f of x is going to be positive for all x's, where x starts to be defined at 3. I wouldn't read a whole lot into it. Why does x or n start at 3 here? It kind of has to, because if we throw a 1 or a 2, we're kind of in trouble here, because we're going to have an imaginary number. And remember, there is no I in calculus, or at least the calculus that we're learning. Actually, it's really calculus. C-A-L-C. Yeah, there is no I. So if we look at number 2, f of x is indeed continuous, because if we were to let x be 3 or bigger, we don't have 0 in the denominator, nothing unusual happening there. And then we do take our derivative, and if I go a little too fast here, and you have to pause the video to kind of catch up, see how this derivative process works, feel free to do that. But by and large, it's really the same process that we just used in the previous example. We have to use the product rule in conjunction with a chain rule approach, and then we have that very common factoring step. Notice between this term and this term, we can factor out the smaller of the 2 exponents, which would be the negative 3 halves, and that would leave us with 2x minus 5 to the first minus x, which you can see simplifies fairly nicely. But what's going to happen is that we notice that if x was 3 or 4 or 4.5, which really isn't going to be applicable because our n values are only going to be whole numbers. We've got some nice decreasing behavior because f prime is clearly negative. But what happens if x becomes 6 or 7? Then we have an issue, and that the derivative of f is going to be positive. Therefore, our no longer decreasing. In fact, this function is certainly increasing for values of x that are larger than 5. And that just simply means that since all three of the criteria are not satisfied, the integral test cannot be applied in this situation. Down the road, what that really means, you're going to have to use another test, and the test we would use just isn't quite taught yet, but it's coming up really soon in one of our next topics. So what are the key points to remember? Number one, when trying to implement the integral test, it's very important to ensure that all three of those conditions are met. There was an advanced placement calculus BC exam just a few years ago where the students did have to state the three conditions. Now, it's likely that you may only need to state three criteria. I mentioned that the value of a sub n is positive, continuous, and decreasing on a free response question. It's probably safer to show the function that represents your interim expression is decreasing. I could see the possibility of them asking you, how do you know it's decreasing, and then throwing in some ideas from AB calculus. So it's not a bad idea to prove that if you're not sure. And then number three, it's also okay if this is not your favorite test at this point. You're going to learn some more conditions tests that may be quicker and may be easier than the integral test. I don't dislike the integral test, but there's several more that I like. I hope this helps. We're going to take a look at another video with topic 10.4 here coming up that's going to actually use the integral test, so be sure to check it out. In the meantime, keep working. Welcome back, BC Calculus students, to video number 2 covering topic 10.4, all about the integral test for convergence. If you got a chance to check out video number 1, we talked about the conditions that must be met in order for you to use this particular test. apply the test to determine if we have convergence or not. Once again, my name is Tony Recker. I'm an AP Calculus teacher at Avon High School, a very large high school west of Indianapolis, where I have the wonderful pleasure of teaching up to 300 students that are in our AP Calculus program with my esteemed colleague. And it's great to share this time with you and help you on your journey to the AP Calculus. So as I said before, what we are going to learn is this integral test for convergence. So if you recall from the previous video, maybe from the notes that you maybe have used in your particular class at this point, the integral test begins with defining this function f that's positive, continuous, and decreasing for some x greater than or equal to n, where n is a positive number greater than 1. Now what that really means is if we don't have a positive, continuous, decreasing behavior for right when x is 1, it's okay. Maybe at 1, 2, 3, we might be decreasing, but as long as we turn that around, if we're increasing from 1, 2 to 3, and then all of a sudden we start to decrease, that's perfectly acceptable. We just have to make sure that we maintain that behavior the rest of the way. So that's why I kind of reword this and say where x is greater than or equal to n. So what we have here is that the summation of a sub n as n goes from 1 to infinity, and the improper integral of f of x from 1 to infinity are going to do the same thing. So if you're really good with working improper integrals into the mix, and if you can tell whether those converge or diverge, then you're going to be able to answer that same question without your infinite series. Again, there are 3 conditions that must apply. I want to restate that. You have to have our function be positive, continuous, and decreasing. If those are not true, it's a waste of time to use this test. So let's practice here. We've got an example here where we're asked to use the integral test to determine the convergence or divergence of the summation as n goes from 1 to infinity of n over n squared plus 1. If you checked out 10.4 AP Daily video number 1, this guy looks pretty familiar because we showed that the integral test can be applied. So I'm not going to go through that again. We know that it works. We're going to dive right into it and figure out if this converges or diverges. So we'll go ahead and let the interim expression be a function f of x defined as x over x squared plus 1. Now, here is where we set up our improper integral. So what's great about this is that you're starting to study and prepare for the AP exam by revisiting this idea that occurred all the way back in Unit 6, improper integration. So how do you set up an improper integral? Well, the way that I like to do it is to make sure that we don't defy the fundamental theorem of calculus, which says they really don't like it when there's an infinity as a boundary. So we can outsmart the problem by putting some arbitrary constant there. I always use b for my upper boundary constant that I change. You really can use any letter that you want. I would like you to maybe consider staying away from x, if at all possible, but any letter typically would work. And I'm just going to outsmart it, like I said, by letting that be approach infinity. All right, so what do we do from here? Well, we hope that we can integrate this x over x squared plus 1. And we can do that by using u substitution. You need a little refresher with u substitution here, which is also back in Unit 6. We would want to let the u be the denominator, x squared plus 1, because we know his derivative is 2x. Swing that dx over, and that basically means that we can offset with the reciprocal of this 2, and we're just integrating a 1 over u form with respect to u.
Well,
hopefully that makes sense. If it's bothering you a little bit, you could probably check out some videos over at New Substitution way back in Unit 6. So what do we have here? Well, we know that that's going to equal the 1/2 times the natural log of the absolute value of u. So we rewrite that expression by replacing our x squared. I'm going to go ahead and keep it in absolute values, although I probably could have survived without the absolute values because x squared plus 1 is always going to take on a positive value. So let's evaluate our boundaries by plugging in b and plug in 1, and notice that we will subtract. And then what we notice here is that if we do let b approach infinity, well, there's no chance of avoiding it. The natural log of b squared plus 1 is going to become the natural log of infinity, and the graph of infinity is just going to gradually get bigger and bigger and bigger as x gets larger, and so we have an infinite answer. So that means that this improper integral diverges. We did lots of problems like that back in the improper interval days. All that you have to do is just connect that to the same behavior applying for the series. And I always like for my students to write that series diverges, right? You don't want to just leave it off right here. We got to be able to connect the fact that just because you know that the improper integral diverges, that's not where the problem stops. So state that the series diverges, and you'll be all set to go. Full close. Take a look at another example. This time, we're going to look at 1 over n squared plus 1 as n approaches, goes from 1 to infinity. Now, I'm going to go ahead and make the assumption here that we have not really looked at this one yet, so we probably want to apply the tests. In other words, we did not see this problem coming from our video number 1, so I better check the criteria. So I noticed that yes, f of x is indeed positive for x greater than or equal to 1. That seems pretty logical. And I would say that the function's continuous because you don't see any risk of having a 0 denominator for any certain values of x. But we better check out the decreasing possibility. So I will rewrite this function as x squared plus 1 to the negative 1. Luckily, this one's got a little bit easier derivative to take. We do need to use the chain rule, as you can see. And then if we clean it up a little bit, you start looking at it and think, yeah, I'm pretty sure that if x is any number greater than or equal to 1, that this function is going to decrease. So I'm feeling good. I think the integral test does indeed apply. So let's use it. So we're going to take a look at this function again. All 3 criteria have been verified. We're going to go ahead and set up our improper integral. Once again, you start with 1, go to infinity. If you want to go on, you start with 1. Just make it easier on yourself. Start wherever your index is. Now, we're going to set it up the same way that we did before, using the arbitrary constant b. Outsmart this problem, let b approach infinity, and then basically now we just have to know what is the antiderivative of 1 over x squared plus 1. Another great way to review some of your integral formulas. Hopefully you all remember that that is the inverse tangent. Inverse tangent of x over 1. So that limit's going to come out in front of the inverse tangent, and we're going to evaluate it from an upper boundary of b to a lower boundary of 1. Once we plug in b and 1 and subtract, we're going to get something that looks like that. We're going to let b approach infinity, and what we're going to get is pi over 2 minus pi over 4. Now sometimes that might be this. Like, where did that pi over 2 come from, Mr. Record? What's going on? Well, if you think about the graph of inverse tangens, you may not be really super familiar with, because you don't really use it all the time. Maybe once you've left your trigonometry class, it just shows up every now and then on top of this. But it's a good idea to know that if tangent has vertical asymptotes of pi over 2, also known as negative pi over 2, then the inverse tangent is going to have the same horizontal asymptotes of pi over 2 and negative pi over 2. And what that means is, as this value of x gets larger and larger, the ceiling becomes this pi over 2. And so it's a really good thing to memorize. The inverse tangent of infinity is basically pi over 2, although that's a pretty informal way to say it, but we'll let that slide for a moment. And now, the inverse tangent of 1 you're talking about there, what angle measure would have a tangent ratio of 1 divided by 1? And that's always going to be a 45 degree angle, which is pi over 4 radians. And of course, if we subtract those, we get pi over 4. Now, what that means is, we have a finite answer, which means our improper interval we know converges, which therefore means our series converges. Caution. You don't want to assume that the series converges to pi over 4. In fact, it very well does not converge to that value pi over 4. So don't equate the value of the improper interval with the sum of the series, because it very rarely, if ever, is going to be equal. We can just say that series. So what are our key points to remember with the inverse test? Well, number one, once we know that the inverse test will apply to a given series, we just simply need to write an improper interval that resemble that series. Make sure that we do a good job, show good minimization so that we can earn all the points if it's a proven unit function. And number two, if that improper interval results in a finite value, and thus we know it converges, then that means that infinite series converges as well, but not necessarily to that finite value as we pointed out in the last. And then finally, if the improper interval does not result in a finite value and thus diverges, then the series will diverge. Once again, we thank you very much. We're going to be pushing on into topic 10.5, and we're going to introduce yet another test in the upcoming videos. I'm sure that you'll stick around. But in the meantime, don't give up. Keep working, because every day that you work with the series, it's going to get better. We'll see you next time. here.
only release at 4, that's why I'm down here. But here I am, and I still want to say it for you. Office for you.
I didn't say too much in this one.
No, but I said, we read a lot of stuff like in history and ask you questions about my mom. Yeah, I'm just enjoyed the little support, and I'm like, well, working tonight, and I'm like, okay. That's why I was down there.
Yes, ma'am.
Welcome back, BC Cal students. Mr. Record here. We're going to be taking a look now at topic 10.5, which introduces the harmonic series and probably more importantly, the P series. A very, very powerful series test that you're going to be able to use all throughout your understanding of series. So basically, in a nutshell, in this video, we're going to determine the conditions for which these types of series will either converge or diverge. My name is Tony Record. I'm an AP Calculus teacher at Avon High School, located in Indiana. So what are we going to learn? Well, first of all, it would be nice if we talk about exactly what is this P series. Well, by definition, a P series is just an infinite series that has a certain look to it. And as you can see in this green box, that look is pretty undeniable. You've got a summation as n. Maybe it starts at 1. It doesn't necessarily have to. It could start at, say, 2, 3, or 4. It's very likely that it's not going to start at 0 in this particular situation. And it's going to, of course, end at infinity. And it's over 1.
Hey mom, did you want to go to the Maranatha Mark thing? Did you want to go to the Maranatha Mark this morning? Um, 8:30 to 9:20. Listen to 10:20. No, I want to go. Wow.
off, and then start seeing something. And then do, otherwise do too.
Everybody.
Otherwise,
Broccoli. Someone is loaded. almost thought it was over.
metric series, for example, if I have the infinite geometric series starting at n equals k to infinity of r to the n, which would be r to the k plus r to the k plus 1 plus r to the k plus 2, and keep going on and on and on forever. There's a few things we've already thought about here. We know what the common ratio is. So the common ratio, which is the ratio between consecutive terms, is going to be r to the k plus 1. Actually, let me just write this as r to the n plus 1. I don't want to fixate on this k right over here. So r to the n plus 1 over r to the n. Well, this is just going to be equal to r. Anything to the n plus 1 over that same thing to the n, that's just going to be equal to r, or r to the first power. You see that here. When you go from one term to another, you are just multiplying by r. And this is all review. If it's not review, I encourage you to watch the videos on geometric series. And what's interesting about this is we've proven to ourselves in the videos on geometric series that if the common ratio, if the absolute value of the common ratio is less than 1, then the series converges. And if the absolute value of r is greater than or equal to 1, then the series diverges. And that made sense. We've proven it as well, but it also makes logical sense that, look, if the absolute value of r is less than 1, then each term here is going to go down by that common, or it's going to be multiplied by that common ratio, and it's going to decrease on and on and on and on and on. And so it makes sense that even though this is an infinite sum, it will converge to a finite value. Now, with that out of the way for review, let's tackle something a little bit more interesting. Let's say that we want to figure out whether a series like this, starting with n equals 5 to infinity, of, let's say, n to the 10th power. The numerator is growing quickly. N to the 10th power over n factorial. And factorial, we know, also grows very, very quickly. Probably it actually goes much faster than even a high degree polynomial like this, or a high degree term like this. But how do we prove that it converges? We can definitely use the divergence test to show that this does not diverge, but how do we prove that this actually converges? And maybe we can use a little bit of our intuition here. Definitely use the divergence test to show that this does not, that it converges. We can definitely use the divergence test to show that this does not diverge, but how do we prove that this actually converges? And maybe we can use a little bit of our intuition here. Well, let's see if we can come up with a common ratio. So let's see if there's a common ratio here. So let's take the n plus 1th term, which is going to be n plus 1 to the 10th power over n plus 1 factorial, and divide that by the n term. So let's divide that by n to the 10th over n factorial. Well, dividing by a fraction, dividing by anything, is equivalent to multiplying by its reciprocal. So let's just multiply by the reciprocal. So times n factorial over n to the 10th. Remember, all I'm trying to do is exactly what we did right over here. See if there's some type of a common ratio. Well, if we do a little algebra here, n plus 1 factorial algebra is always fun. This is the same thing as n plus 1 times n factorial times n factorial. You're not used to seeing order of operations in the factorial, where this factorial only applies to this n right over here. And why is that useful? Because this n factorial cancels with that n factorial, and we're left with n plus 1 to the 10th power over n plus 1 times n to the 10th times n to the 10th. So I know what you're thinking. Hey, wait, look, this isn't a fixed common ratio here. The ratio between consecutive terms here, when I took the n plus 1th term divided by the n term, it's changing depending on what my n is. This ratio, I guess you could say, is a function of n. So this doesn't seem too useful. But what if I were to say, okay, look, in any of these series, we really care about the behavior as our n's get really, 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 really large, as the limit as our n's go to infinity. So what if we were to look at the behavior here, and if this is approaching some actual value as n approaches infinity, Well, it would make conceptual sense that we could kind of think of that as our what the tweak is. It's tweak over n plus 1 times n to the 10 times n to the 10. So I know what you're thinking. Hey, wait, look, this isn't a fixed common ratio. Here, the ratio between consecutive terms here, when I took the n plus 1 term divided by the n term, it's changing depending on what my n is. This ratio, I should say, is a function of n. So this doesn't seem too useful. But what if I were to say, okay, look, in any of these series, we really care about the behavior as our n's get really large, as the limit as our n's go to infinity. So what if we were to look at the behavior here, and if this is approaching some actual values, n approaches infinity, well, it would make conceptual sense that we could kind of think of that as our, what the common, the limit of our common ratio. So let's do that. So let's take the limit as n approaches infinity of this thing. So remember what we're doing here. This isn't just kind of some voodoo. Conceptually, let me copy and paste this. Conceptually, we're just trying to think, well, what is the common ratio approach? What is the ratio between consecutive terms, the n plus 1th term and the nth term, as n gets really large? And what we see here is we have this up here. We don't have to multiply it out. This is going to be n to the 10th plus a bunch of other stuff. It's going to be a 10th degree polynomial. And this down here, this is going to be, actually this one we can figure it out, this is going to be n to the 11th plus n to the 10th power. So the limit as n approaches infinity, well, this denominator is going to go faster than that. We could divide the numerator and denominator by n to the 10th, and all of, and everything, well, you could divide, actually, the numerator and denominator by n to the 11th, and everything up here is going to go to 0, and this is going to be 1. And so the limit right over here is the limit. This limit is going to be equal to, this limit is going to be equal to 0. As n approaches infinity, one way, the ratio between consecutive terms approaches 0. So this seems, if you use the logic from our common ratio up here when we look at geometric series, this is clearly not a geometric series, but it would say, well, look, as n gets really large, the ratio between consecutive terms gets smaller and smaller and smaller. Hey, maybe we can make the same conclusion. Maybe we can make the same conclusion that therefore the series actually converges. The series actually converges. So n factorial converges. So can we make this statement? And the answer is yes, we can. And what allows us to do it is the ratio test. Let me write that down. The ratio test. And all the ratio test tells us is if we have an infinite series, and I can say from n equals k to infinity, and the answer is yes, we can. And what allows us to do it is the ratio test. Let me write that down. The ratio test. And all the ratio test tells us is if we have an infinite series, and I can say from n equals k to infinity, and if we take the limit as n approaches infinity, of the absolute value of a to the n plus 1 over a to the n, and over here I get the absolute value of that limit, but we absolutely could have taken the absolute value of that limit, and these were all these terms right over here were positive, so the absolute value is the same thing. Now, if this approaches some limit, once again, this limit is what is going to be our ratio between consecutive terms as n gets larger and larger. The ratio tells us if L is less than 1, which is the situation here, L is clearly less than 1, then the series converges. Some definitions say it's absolutely converges. It will convert absolutely. The absolute value of the series converges, and then that also means the series itself converges. If L is greater than 1, series diverges. And if L is equal to 1, it's inconclusive. We don't know. You have to do some other test to prove whether it converges or diverges. So that's the essence of the ratio test. Find the absolute value of the ratio between consecutive terms. Take a limit that approaches infinity. If that approaches an actual limit, and that limit is less than 1, then the series converges. It's really based on the same fundamental idea that we saw with the common ratio of geometric series.
see you later.
Sure.
If you have this 1 over n that's raised Welcome back, AP Calculus BC students. We're now into topic 9.2, and we only have one short video to introduce this idea of taking the second derivative of a parametric equation. So I think the title pretty much says it's what the video is all about, but we are going to demonstrate how to find that second derivative, and we're going to use it also to talk about an idea from a previous unit, the concavity of a graph. So again, my name is Anthony Record. I'm an AP Calculus teacher from Avon High School, located just west of Indianapolis, and it's always a pleasure to be with you all. So what is it that we're going to learn here? Well, the first derivative of parametric equations. Well, wait a minute, we already know that. Well, we probably ought to look at this one more time just to make sure that we've got it set in stone, because you have to take the first derivative before you can take the second derivative. And that's pretty much been the case all along, ever since we learned higher order derivatives. So I bet this looks familiar to you if you've been following along with AP Daily, especially from topic 9.1. dy dt all over dx dt. So formally we would say the derivative of y with respect to t divided by the derivative of x with respect to t. Now our interest is going to shift to the second derivative of the pair of parametric equations. And the result may surprise you. So if you're getting ready to turn this video off thinking, hey, I know what's welcome back, AP Calculus BC students. We're now taking topic 9.2, and we have one short video to introduce this idea of taking the second derivative of parametric equation. So I think the title pretty much says what the video is all about, but we are going to demonstrate how to find that second derivative. We're going to use it also to talk about an idea from a previous unit, the concavity of the graph. So So again, my name is Anthony Record. I'm an 85 teacher from Avon. I still take this class with my and all these things. So what is it that we're going to learn here? Well, the first derivative of parametric equation. Well, wait a minute, we already know that. Well, we probably ought to look at this one more time just to make sure that we've got it set in stone, because you have to take the first derivative before you can take the second derivative. And that's pretty much been the case all along, ever since we've learned higher order derivatives. So I bet this looks familiar to you if you've been following along with ABA, especially in topic 9.1. dy dt all over dx dt. So formally we would say the derivative of y with respect to divided by the derivative of x with respect to. Now our interest is going to show the second derivative of the parametric equation. And the result may surprise you. So if you're getting ready to turn this video off and hey, I know what's the second derivative, I wouldn't do it because these guys are a little tricky. Alright, maybe now you think this is. So what is the second derivative of the parametric equation? Well, let's say that we're given x equals x of t and y equals y as 1. And we know that the second derivative of y with respect to x is very often presented using this type of notation. Right? This is our standard Leibniz type of notation that I'll lead you here in a moment. And what that really entails is the fact that we want to take our derivative of y with respect to x, and we want to take another derivative. So we're going to apply this derivative function, the derivative of all of this with respect to x. Seems to make sense. Well, that's why the notation looks the way it does, in case this has never been explained to you. Why is the 2 located there after the d? Well, it's sort of because there's a couple of d's right there hanging out. Don't want you to think of it as d squared, because that is definitely not true. But it has the same idea, 2 d's up here. Likewise, if you were to multiply by the reciprocal of this dx, there's a pair of dx's hanging out, and that's what this means. Dx appears twice. We sort of think of dx being one package. Delta x, change in x, dx is the same thing. It's like this one package. Alright, well, what are we going to do then? Well, the standard second derivative notation is not lost on us because we've seen that perhaps before when we were discussing higher order derivatives of AB. But when we're talking about doing this with respect to a parametric equation that's in terms of t, you have to think about differentiating with respect to t. And so basically, and most people out there aren't going to like this if I say divide by dt, the top and divide the bottom by dt, probably not the best way to explain it. It's very similar to the mathematical process that I just described. We're going to place these dt's in the top and the bottom to balance this particular fraction expression, and then that is going to allow us to do what we need to do. Differentiate with respect to t, because isn't that what dx dy dx is in terms of? So let's practice. So we're going to go ahead and find the second derivative of y with respect to x. So to do that, we start by taking the derivative of y on top, which is 8t cubed, and the derivative of x on bottom. But we're pretty easy today. We'll simplify, and now we're moving on to our second derivative. Now, it would be so easy just to assume that that derivative is the derivative of the 4 thirds t squared, which is 8 thirds t. But we know that 6t has just got to show up in that denominator because it's part of the definition of this second derivative. And hopefully the notation in the previous slide makes sense. And if not, just rewind the video, go back and watch it again, and pay very close attention to that 6 slides during this presentation. Of course, we can go ahead and do a little simplifying here and multiplying by the reciprocal, and we see that pair of t's cancel out, and we get the constant, which isn't always the case, just so happens to be the case in the final. Again, you're going to hear me say this a lot. Your teachers are probably going to be happy that I'm saying this a lot, but take note that the denominator 6t is absolutely required in order for you to have a correct second derivative. Let's take a look at example 2, which is shrouded in this multiple choice problem. It's a little bit diabolical, and we'll see why in a second. So we're going to find the second derivative of y with respect to x, and we're going to evaluate it at the time for t value 5 or 6, just right next to value 6. So again, your first derivative is nothing new. You take the derivative of y, and you take the derivative of x. And remember, the derivative of tangent is secant squared. Now at this point, we can go ahead and change that secant squared to 1 over cosine squared, and we can perform a little bit of a multiplication by reciprocal. And I think getting a cosine cube is going to be a lot easier to deal with than trying to take the derivative of cosine over secant squared. Alright, let's dive into our second derivative. We start by taking the derivative of first derivative with respect to t. Now that's a pretty tricky chain rule. Hopefully you follow that. If 3 comes out in front, cosine is now raised to the second. And of course this piece right here is your chain rule piece, du dt, and you take the derivative of cosine of t there. Alright, now what comes next? Don't forget, you'll need that secant squared there in the denominator, or 1 over cosine squared if we're probably going to refer to it as just a little bit. If you go ahead and simplify by bringing that secant squared up on top as a cosine squared, we really have 3 cosine to the 4th. All we need to do now is evaluate the second derivative from pi, t is pi over 6. So we just replace those t's that we see with pi over 6. Notice I went ahead and multiplied the 2 cosine squares together. And hopefully you're okay with the fact that cosine of pi over 6 is the radical 3 over 2, and the sine of pi over 6 is the 1 over 2. And if we simplify that just a bit further, the square root of 3 to the 4th is 9, the 2 to the 4th is 16. And if we clean it on up, and you get an answer that, hey, matches one of our choices. That's always a good thing, isn't it? But the little diabolical trick here, you look at choice A here just a little bit. Choice A represents the distracted choice that would omit the dx dt here in the denominator of the second derivative. Basically, you would have had this cosine to the 4th and it would only been squared, which would have caused the square root of 3 over 2 squared to be 3 over 4 here. And if you do all the arithmetic there, you would have negative 9 over 8. So, hey, that's a development thing's not a feature. But they do want to make sure that you understand your calculus very well. And this choice A does represent a very common misconception, so be very careful. All right, let's take a look at our third example. Consider the Greenwich equation x of t is t squared, y of t is t cubed minus 4t. Find the integral of t for which the graph of the Greenwich equation is concave problem. So again, sounds like a broken record here. We're going to go ahead and pick dy over dt divided by dx over dt. And there we go, 3t squared minus 4, 2 times t. And now we simplify this a little bit. Again, I'm going to try to avoid doing a complicated quotient rule derivative when we can avoid it. Since we have a monometer denominator here, we'll just void it apart into 2 terms. All right, second derivative time. Differentiate our dy dx that we found up above. And then throw that 2t in the denominator, all important 2t. Simplify this in a very similar fashion. Basically, the 2t multiplied, reciprocate and multiply the denominator. This is 2's that cancel away, and then a t squared times t in the bottom is t cubed. And there's a second derivative. Now the problem with that is that it's pretty hard to handle. So if I get a common denominator, it's going to help us out here just a little bit. And then we have to think about how do we determine when a function is concave over 1. We have to look at the sign of the second derivative, which means we have to find these values for which the second derivative is either 0 or 1. So if I set the numerator equal to 0, then we have to define when the derivative is undefined. I'll get no solution to this in a real number system. However, the denominator set equal to 0 will certainly give me a t equals 0 result. All right, so what does that all mean? Well, if 0 is my value that I can test around, it seems like naturally test a very close pair of t. So how about negative 1? So I'll just plug negative 1 into our second derivative, and I get 3 times negative 1 squared plus 4 over 4 times negative 1 cubed. And that will result into a negative 7 fourths, which of course is negative. How about we test something on the other side of 0, like positive 1? Do the same type of calculation, and you can probably guess this is positive 7 fourths, and that would be what we want here, because oddly enough, is height when the second derivative is positive. Now, just really quickly, we want to take a quick glance at this graph. We can verify these findings. Because in the sketch, t equals 0 is located right here. And this graph actually starts here from the bottom, and then it kind of moves around like this. And remember, we discovered that from time t equals 0 to time infinity, to the right side of t, we have this nice concave complement as our analysis of the derivative. So, key points to remember: the most common misconception of the second derivative of the Greenwich equation is c equal to mid that dx.
Alright, I'm in issue right now. See, let's go.